So, with that high level discussion of the concept of smart contracts, now we will try to get our hands dirty and do some practical hands-on work with smart contracts. What we will try to do is to build a smart contract in one of the most popular languages called Solidity and deploy it on blockchain and also see it working. Before we get into our discussion on how we will do it, I just want to highlight some high level points about what we are going to try to do. So, we will build a smart contract for the Ethereum blockchain. We will compile it and then we will deploy it on the Ethereum blockchain and we will also interact with it. As we've already discussed, smart contract is a piece of code that is deployed or copied onto the blockchain against a specific address or a specific location, and then different nodes or clients to the blockchain execute transactions that call that smart contract and update its state or read its state. So, the first thing that we have to understand is the concept of state. Although we've already discussed at a high level what is meant by the data that's stored on the blockchain, but from the standpoint of Ethereum, we have to understand that Ethereum captures state in two different ways. One is the state that is captured against your address, which is mostly the transactions and the balance that you have as a result of that transaction. The other is the state that is there with your smart contract. So, if we mimic or if we try to understand smart contracts from the perspective of code or logic that works on data, then blockchain with its data is that data set that one has to work with, and the smart contract is the business logic, and that data is also called state. So, every time I interact with the smart contract and update the state of the blockchain, I have to send a transaction. But if my interaction with the smart contract is limited to reading the state, then I don't have to send a transaction. There is a simple observation call that I make that gives me a view of the state. So, having said that, I will translate this simple logic of updating state and reading state in a very small and easy to understand, almost trivial smart contract that is going to represent these two interactions. And once I build it, I will use my private keys to sign a transaction that deploys the smart contract. I will see it on the blockchain and I will try to interact with it. So, there obviously is a lot more to smart contracts than just reading and writing state, but from the scope of this discussion and its objective of a simple and concise start, we will just aim to do these two things as a part of our initial steps or initial understanding of smart contracts. For those of us who want to understand Solidity in detail, a good source is docs.soliditylang.org. You have the latest version 8.6 documents that you can refer. But just to give you a high level guideline, Solidity is very much like a normal programming language. For those of us who are familiar with Python or JavaScript, will find it very easy to use, and most of what you do in other languages is available in Solidity. The points of difference are that Solidity has to be written with the transaction fee and the limitations on complexity in mind. But we will get to those constraints as we discuss more and more about smart contracts in our advanced stages. So Solidity provides a very wide set of tool set that you can use to develop smart contracts. The easiest one is the Remix Solidity browser. Remix is a browser component or website that hosts the entire integrated development environment for building smart contracts in Solidity. It lets you build smart contracts with its own test blockchain. Then it lets you deploy smart contracts on real blockchain instances also. And it's got an intuitive environment. It is a recommended tool for the beginners. Obviously, when we get more advanced in our development skills, then we will take a look at some of the other tools like Truffle or Hardhat, or if we're talking about Hyperledger, then Hyperledger's own integrated development environment to build smart contracts. So before we start coding, I want to get into a quick discussion on why we choose Ethereum as our platform for demonstrating simple smart contracts. And there are many reasons for that, but the first one is the ease of getting started. What you will notice is that I will be able to build a smart contract and deploy it and test it without needing to install anything on my machine. One of the most difficult things or challenging aspects of building on any technology is that there is a big starter's learning curve, and then there is a very big environment dependence. If I have to start developing code on or chain code on Hyperledger, then I would have to set up a very big environment which involves setting up Go language, setting up Python dependencies, setting up Hyperledger's own instance through Docker. So all of those form barriers for someone who just wants to start developing right away. Obviously, there are test environments and test tools, but if we're talking about Hyperledger, it does not have a public blockchain. It's a private blockchain platform, which means to some extent we are ourselves responsible for building the environment on our machine and then working with it. This limitation does not exist with public blockchains, because with most public blockchains there is the mainnet, which is the actual blockchain network, and then there is the testnet. What testnet does is it gives you a very close simulation of the mainnet. The reason why testnet exists is because mainnets with its own cryptocurrency and cryptocurrency's financial or dollar value, there is always a chance that when we are testing out new code, we can compromise that money or lose that money, because uh, that cryptocurrency interaction is also a part of building smart contracts. But that testnet with its reason to exist also help us um, in not requiring our own environment. So when I talk about Ethereum, it's got its 3 or 4 test nets that anyone can use to build their own contracts and test them. So apart from just reducing the risk of money loss, test nets also reduce the risk of uh, any blockers that one might encounter as a part of building up the environment. So we will use that leverage and we will build a contract and deploy directly to the testnet. Had the testnet not existed, we would have had to set up our own blockchain on this system, which would have taken us a good amount of time. We will do that as an exercise, but for the objective of building smart contracts, that is not necessary. So having said that, the first thing that we want to do is build the contract, and to build it, let's first try to understand the Remix environment. So on the left side you have the file explorer, which shows you all the Solidity files that are going to be a part of your contract. So there is a specific structure of the files. There's the contracts directory in which you have 3 contracts. There are scripts that let you deploy it. These are JavaScript scripts. And then there is a test file that lets you test your Solidity code. We will not go further in depth on in what this structure means. It has some implication when we start building out end-to-end smart contract solutions, also called the dApps. In this session, we will just take a look at the contracts that we'll build. So we are just interested in this contracts directory. So anyone who will launch Remix will get this default sample of the smart contract projects, and they can take a look at all the contracts that are already available, ready for them to use. So this is your file explorer. On the right hand side you have some quick links and some plugins. For now we can ignore them. Right below the right corner you have the console. So this console will show you the activities that happen when you build your smart contract, you deploy it, you interact with it. It will show you the transactions that you're sending and the result of those transactions, and some debug points. So it's a good good way to trace the activities that are happening with your smart contracts. Then we have on the extreme right a panel that gives you different views. So we have the file explorer view, then we have the compiler view, then we have the deploy and test view, which is going to deploy and then run your transactions. Then there are some views around Solidity details of how much is the complexity and security measure of your contracts. Then there is the debug view, which we will not get into in this session. Then it also lets you run your test code if you've built any. And then the flattener is a way in which you can convert your entire set of smart contracts into a single file. This flattener is used in a very specific case where you have to verify your Solidity code on the Ethereum blockchain. We will not get into that today. Then 3-box spaces, it's a specific plugin for a specific functionality, again to avoid complexity. We'll not discuss that today. Then there is a way in which you can fetch existing deployed contracts. We will not see this functionality today. And then there is the plugins list. This list lets you activate plugins that are already available in your environment. Plugins are just additional functionality provided to you in case you want to use it. So let's go back to the file view and let's take a look at this very simple storage smart contract. So as you can see, it's a very small contract, around 28 lines, and it's got some comments which are appearing in gray here. These are the comments, and then it's got some 6 or 7 lines of code. So let's ignore the contract comments for now, and let's start with the actual code. For those of us who are familiar with C++, you'll understand what is meant by the pragma directive. So out here, pragma has just one value, Solidity, and then it's got the versions that your contract is going to support. So what it means here is that the version can be greater than or equal to 7, or it can be less than 9. So all Solidity versions between 7 and 9 are supported for this contract. So what we mean by versions here is the Solidity compiler support. Solidity has very frequent releases of compilers that have bug fixes and optimizations, and one has to be careful of which compiler version they are supporting to ensure that their contract compiles correctly, and then there is no unexpected outcome. Before we get into what this code is going to do, I just wanted to get into how Solidity works, or for that matter, how Ethereum smart contract lifecycle works. So once we are in this environment and we build this code that's already built out for us right now, the next step for us is to compile this code. So compilation again is a fundamental concept in programming where the source code or your business logic file or business logic set of files, they are converted into a file or converted into an artifact that the system understands. So right now, if I have this smart contract and I want to ask the blockchain to run it, blockchain does not, or the environment in blockchain does not understand what is meant by this language. It understands a different set of instructions, which is called bytecode. So something similar happens in the case of legacy programming languages like C, C++, which gets compiled into machine language or assembly. Got Java, which gets compiled into bytecode, which is again a set of instructions that is understood by the Java virtual machine system. Something very similar happens here. So Ethereum and the way it's built is that uh, the environment or the execution system that runs smart contracts is built within Ethereum as a virtual machine. What is meant by a virtual machine is that it is an instance of a system that is able to understand and run a specific set of commands that are detailed as a part of this as a part of its own specifications. So it's very similar to the concept of containers. So when we talk about virtual machines and containers, there is not a lot of difference between the two. For those of us who are familiar with either concepts will understand what is meant by virtual machines. So Ethereum also offers a similar environment called the Ethereum Virtual Machine or EVM. When we develop code for Ethereum, we will reuse the word EVM very frequently. So in this case, what will happen is when I compile this contract, it's going to get converted into what is called the bytecode. And that bytecode is something that we will copy onto the blockchain as a part of deployment. And when the blockchain receives that bytecode, it's going to create an address for it, and that address will be returned to us. Now, before we get into the flow of deployment and testing, let's first try to understand this very basic contract and the two activities that it's supposed to represent, as in creating or saving the state and reading the state. So we've already seen the pragma directive. The actual code that represents the contract starts with the word contract. It's very similar to the word class in C++ or Java. So this is where your code starts from, and then you have to give a name to your contract, which is being called storage here. So all the reserve words which are specific to Solidity, they will appear in a different color. So you've got unsigned integer to 256 in a different color. Then number is the variable name that we've declared as of the type unsigned integer. So this uint 256 means it's a specific type, and then we've got two functions, store and retrieve, and this is your entire smart contract. So with the assumption that we are familiar with what is meant by variables and what is meant by functions or methods or routines, I will assume that the general structure of this contract and what it's trying to do is clear. It's actually very intuitive if you think about it. It's got one number that it's declaring, and then it's got a function that stores a certain value in that number. It accepts the number, and then it assigns number to what it's accepting as a parameter, and then it is of the type public. The other function is not doing any assignment. It's got no parameter. It is returning the state, which is the state on the blockchain called number. So when I will deploy this contract and call store and provide a specific number, then that number will become the part of the state of the blockchain. and the way blockchain is structured is once this becomes the state, it cannot be changed. It will always be appended to, and that is a concept that we had discussed in our earlier um, conceptual sessions on blockchain. So as a concept, it's very easy to see what we are trying to do here. The simple things that you could notice is that every function is preceded by function name, followed by parameters, and then the type of function. There are other types as well. You could declare it as a private or an internal function, in which case it cannot be called from outside of the blockchain, in fact outside of this contract, or you could declare it as public, which is what we've done here. Then if you look at the retrieve function, it's also got another definer called the type of function, and it's a view type of function, which means that this function does not need a transaction. It's just creating a view of the blockchain state. And then it's got returns. Returns means that it's going to return a certain type, which is going to be unsigned integer 256. So bear in mind, we are not in this session attempting to understand the syntax of Solidity end-to-end. What we just want to do is to see how smart contracts work from a conceptual high level standpoint. So once we have all of this built out, there's not a lot of connection of this contract with anything else that we've got in terms of the project, other project artifacts. So we can simply deploy this contract independently and see how it works. So once we've seen it, the next thing we have to do is go to the Solidity compiler section. For compilation, we don't need to connect to any blockchains. This Remix environment automatically loads a compiler for us. So compiler again is a program that converts this source code into a virtual machine understandable code called bytecode. So we have different versions of the compiler available for us to use. There's not a lot to be thought of in terms of which version to use right now, but it will become important when we focus on specific parameters. Then you've got the language. There is another language possible, YUL, again out of scope for us. And then there is the target EVM version. Now this is important to understand in relation to what we have been talking about earlier around virtual machines. So we can ask our contract to be built in a way that supports a specific version or type of EVM. Now one of the things that we need to understand about Ethereum is that it's a very vibrant blockchain with a lot of different version upgrades that keep happening with it, and some upgrades of version result in EVM upgrades also. So if one wants to specifically target a certain version, then that's how you have to do it. Then we've got some housekeeping stuff like auto compile, hide any warnings. You can also enable optimization, in which case the code is going to be optimized. Let's not do that. We want to understand the code instead of building it optimally for now. And then there are some other features that are specific to Ethereum, which we'll not go into right now. So let's click Smart Contract Compile, and what you'll see is it will compile it. Since it's a small contract, it will not take long. Once compiled, you will see that it will appear under the drop down, and once it's available here in the drop down against the contract, your compilation is successful. Now let's see a situation where it will be unsuccessful. So if I, let's say, change and force the compiler to record an error, then it will not show any of the sections that we were seeing earlier around the compiled output. It will clearly tell you that the contract is not compiled. It will give you a warning and the specific error. This warning will not stop the compilation from happening, but this error will. So let's fix it back, and you see that it's automatically compiled again. There is a section here that says bytecode, and this bytecode is what I was talking about when I said that the compiled version is what is deployed on the blockchain. So if you click on it, it will get copied onto your clipboard, and you can paste it on any text editor. So this is that specific bytecode that EVM is looking for. So as you see, it's got a set of instructions, and these instructions represent what we want to do in the contract. So let's go back to the contract. We've already compiled it. Now let's get to the deploy and run transaction section. The first thing you'll see is the environment. So there are multiple ways in which Remix can help us, and the easiest way is to use Remix's own blockchain environment, which is what you'll see is selected by default. So once we've selected an environment, which is going to be the default one for now, the next one you see is a set of accounts that we'll use for testing. So we've already seen how wallets and accounts work. These accounts are pre-created by the Remix environment for us to use, and each one of them has been funded with certain ethers that we can use for our contract interaction. One thing that we'll understand is every time we send a transaction to the contract, we will have to pay some fees as a part of that transaction's validation and verification process. So when we'll work with real blockchains, just to be able to deploy a contract and run that contract transaction, we'll need some cryptocurrency balance in our accounts, and these accounts are what we will have to use as a part of our transaction signing process. So these accounts, they are appearing as real accounts, and each one of them also has an associated private key that is going to be used when we sign transactions. But since this is all internal and happening inside the Remix environment, those keys are hidden from us and are not relevant for now. So gas limit and the value that we'll send with the transaction are things we will not get into right now. What we'll do is we will simply deploy our contract with the press of a button that's available here. So as a part of this deployment, I will see some activity in the console that's going to represent the transaction that we'll deploy, we've got this button that's going to clear the console for us. So I press deploy, and it's created a transaction that represents my deployment. So you'll see a couple of things here. You'll see the status, the transaction has been mined and successfully executed. You'll also see a transaction hash. Now, this transaction hash is important because this is unique for every transaction that we send on the Ethereum blockchain. Even transactions that represent transfer of ethers or transfer of cryptocurrency, or transactions that represent interaction with a smart contract, every transaction has a unique transaction hash. Then we've got the from. From is the account that we use. It will be the one that we select from this drop down. As you see, it's the same one, 5B3 starting. The other thing that you'll notice is that the balance of this account has gone down from 100 to a small difference, and that is exactly the proof of the fact that you have to pay some transaction fees. So every time I will send transactions, this is going to keep coming down. Rest of this stuff is not something that we want to get into right now. So once deployed, what you'll see is there will be another section created here at the bottom that's going to say the contract name, and it's going to have an address. So this address means that the contract is deployed here on the blockchain. And when you drop it down, you will see the two functions that you've implemented in the smart contract. These two functions have been enabled for us to use to test our contract function and its capabilities. So the first thing that I'll do is I'll try to retrieve the state of this number that I've declared. Now, since I've not set any state, my expectation is it will return what is called the default state. Default state in this case is going to be 0. Although for those of us who are familiar with programming, the default state is not always 0 or blank or null. Sometimes it's just the read of a memory, so it could be garbage also. But let's just test what is the default state right now. So as you can see, the default state is 0, which is a good starting state. So it's an integer. If it was a string, the default state would have been blank, and same defaults exist for other solidity types also. So now with the starting default state as 0, I am prompted to change that state to a different number, let's say 23. So once I type my parameter 23, I'll notice that transaction will go through. This transaction will have the same structure as the deployment transaction, except that it will have my input. This input is a part of the parameter that I sent to the contract that I've deployed. Now let's see if I've been successfully able to retrieve, update the state that I'm going to retrieve. So I've retrieved the newly updated state. What this means is that I've successfully been able to execute and retrieve a state that was updated by me as a part of the execute, which is essentially all that we do in any smart contract interaction. We update the state or we read it, but a lot of business logic and complexity is going to be introduced when we build complex applications but they'll all boil down to these two very fundamental processes of updating and reading. So here we've actually added a state. If we change it to something else, that's going to be an update, but it means essentially the same thing. You see the updated state. With this, we've completed one part of our demonstration where we wanted to build a contract and test it completely inside our local machine environment. The next step for us is to use this same flow but deploy the contract on the real blockchain, and we'll be targeting Ethereum testnet for that.